All right, in this example, we want to find the centroid of the region bounded by the curves y equals the cosine of x equals 0, y equals 0, and x equals pi over 2. So let's sketch a graph of this region to make sure we know what region we're actually talking about. We're looking at the graph of the cosine function between x equals 0 and x equals pi over 2. That means we're looking at the first quadrant. So we know that cosine is going to start off at y equals 1 and then decrease down to y equals 0. So our graph is going to look something like that, with x equals pi over 2 over here on the far right. So there, pi over 2. And so we are looking at the area inside this shape right here. So there's y equals the cosine of x, there's x equals 0, there's y equals 0, there's x equals pi over 2. Okay, so we are going to try to find the centroid of this region. In order to do that, we are going to need to take our formulas for both x bar and y bar into account here. Okay, so remember that in general, the x bar and y bar expressions involve the area of your function, right, in the denominator. So let's calculate that first. The actual area of this purple region can be found by integrating the function y equals the cosine of x between 0 and pi over 2. So to find this area, we take the antiderivative of the cosine of x, that's the sine of x, and we evaluate it between 0 and pi over 2. So sine of pi over 2 is going to be exactly 1. Sine of 0 is going to be 0, so we get 1 as a result here. The area of this expression is exactly 1. So now I don't need to divide by this integral every time, I just need to divide by the constant 1, which doesn't change things. So x bar and y bar now can be defined just as their integrals themselves. So we know, for example, that x bar is defined as 1 over the area times the integral from a to b here, so this is going to be from 0 to pi over 2, of x times the function, so x times the cosine of x in this particular case. But 1 over the area is exactly equal to just 1, so we don't need to even take that into account. We just need to take the integral from 0 to pi over 2 of x times the cosine of x. So in order to actually take this integral here, we're going to need to use integration by parts. U is going to be equal to x. Du can then be cosine of x dx. So dv, my bad. dv is going to be cosine of x dx. There we go. So take a derivative and an antiderivative. The derivative of u, du, will be dx. The antiderivative here, v, will be sine of x. Okay, so this integral for x bar here becomes uv, so that's going to be x times the sine of x, minus the integral of v du, so the integral of sine of x dx. All of this evaluated between 0 and pi over 2. Okay, the antiderivative of sine of x is negative cosine of x. So we have minus negative cosine means plus positive cosine. So we end up with x times the sine of x plus the cosine of x evaluated from 0 to pi over 2. Okay, so now let's plug in and see what we actually get for our result here. If we evaluate everything at pi over 2, cosine of x is going to be 0, sine of x will be 1, so we're going to get x is exactly equal to pi over 2. Then when we evaluate at 0 here, we'll get 0 times 0 plus 1. So there you go. We'll have pi over 2 minus 1 for our x bar value here. Pi over 2 minus 1. So pi over 2 is approximately equal to about 1.6. So pi over 2 minus 1 would be about the 0.6 part. So we'd end up right around here for our x bar value. And again, that makes some sense. We'd be further off to the left than we are to the right because most of the area is on the left side and not as much as on the right side. So far this is making sense. Now we want to find y bar. So I'm going to do some erasing, and we're going to calculate y bar here next. Okay, once again, y bar usually is defined as 1 over the area times the integral from 0 to pi over 2 of now 1/2 of f of x the quantity squared. So this is going to be 1/2 cosine of x the quantity squared dx. But once again, the area here for our function is exactly equal to 1. So the 1 over the area part doesn't matter in this case. We can factor out the 1/2 here, and cosine of x the quantity squared is just cosine squared. Now I don't have the antiderivative cosine of x, so I'm going to rewrite this in terms of simpler trig functions. I can rewrite this as 1/2 times the integral from 0 to pi over 2 of 1 plus the cosine of 2x divided by 2 dx. Okay, once again, this is just replacing cosine squared with the power reducing identity here. Now we can factor out the 1/2 again and take this integral in 2 parts. So we're going to have 1/4 times the antiderivative of 1 is just x, and the antiderivative of cosine of 2x here, we can do a quick substitution, right? Make w equal to 2x, so that dw is equal to 2 dx, divide by 2 on both sides, so that we get dx is equal to dw over 2. We're going to have an extra factor of 1/2 here, but then the antiderivative of cosine of w would be sine of w. So we're going to end up with plus the sine of w, or the sine of 2x, divided by 2 here. Okay, so there we go. We have our antiderivative taken. Now all we need to do is evaluate it at our endpoints. A few nice things are going to happen here as well. When we take the sine of 2x at either of these points, we're going to get 0, because the sine of 2 times pi over 2, sine of pi is exactly 0, and the sine of 0 is exactly 0. So this term right here doesn't contribute. Right here, when we evaluate at pi over 2, we're going to actually get the value we want, right? So there you go. You have 1/4 times pi over 2 minus 0. That ends up with pi over 8 for our result here. All right, and so pi over 8 is supposed to be the y-coordinate of the centroid. Pi divided by 8 comes out to about 0.39. So we're looking at a value that's maybe here. There's y bar at about 0.39, give or take. And so our centroid ends up being there. This makes a lot of sense, right? Because again, the bottom of this region and the left side of this region are much larger than the top right sides, right? The top right sides are where we're missing area here. So you would expect that the centroid would be down on the bottom left. And that is exactly what we see here. Okay, so there we go. We have calculated the moments and the center of mass for this shape. So what's left to do? The only thing left to do is, what about regions that aren't attached to the x-axis here, right? The same thing that happened when we started chapter 6. All through chapter 5, when we talked about integrals, we were looking at the area under one curve and above the x-axis. Then we looked at the area between two curves. So that's exactly what we still need to do. So in the next example, we're going to look at the centroid of a region which is not touching the x-axis, of the region between two curves.